Okay, so what we're going to do today is we're going to continue talking about different types of services. If you recall, last class we talked about started services, and we talked about different ways to program them. And I showed you a download image application example that was implemented to use a single background thread, and we talked about some of the subtleties of shutting down those threads using the stop self method. Since that time, I've done some more exploration of that, and I'll show you a bit more about it when the time is right. What we're going to do now is we're going to talk about one way of programming a started service using a built-in framework that's part of Android called the intent service. And you'll see what the intent of the intent service is in just a moment. So we'll basically show how you can use the service, the intent service, which is a framework in order to be able to in order to be able to take requests expressed as intents and process them as commands. So this ends up using a bunch of cool patterns that we'll talk about. You can find more information about the intent service here. Let's first talk about the motivation for the intent service. So as you might remember, when we talked about the download service from the previous class, there's a common idiom that Android uses in a lot of the code, a lot of the packaged applications and other kinds of things that basically simplify the way you process concurrency in a service. And the way it works is that you have this service that has a couple of hook methods in it, like onCreate, onStartCommand, and handleMessage. And these methods are all implemented to work together to take an intent that comes in from the activity, or whoever sent the intent, and use that to be able to put in a background queue and run in the background thread. That's basically the idea. So the code looks kind of like this. This is the canonical way that this works. This appears multiple times within Android source code itself. So you end up implementing the onCreate method of the service, which creates a new handler thread and starts it. And then it goes ahead and grabs the looper of that started handler thread, and it passes it to something called a service handler as a parameter. And that service handler then starts up in a mode where it's going to listen, or it's going to wait for intents to come in on the background thread. That's what the looper inside that service handler is going to do. And then when an intent comes in, the onStart command gets called back. The onStart command turns around, makes a message, populates a few things in the message, like the start ID, which is very important, as we'll see later, and the intent that came in. And it takes that message and it calls send message, and it sticks the message into the message queue that's then going to be serviced by the one and only background thread. The fact that there's one background thread here is very significant. That one background thread waits for something to do. When something happens that it learns about, because it's called back automatically by the Android Hammer framework, the handleMessage method is called back, passing in the message. That calls download image and reply, in this case because it's the download service. And when it's all done, it calls stop self. Now, this stop self thing is really, really interesting. And some people asked some really good questions about it last class. And it's very, very, very subtle. And so we're going to talk a little bit about that later once we talk about the intent service and how it works. But I'll give you a sense of how things work more generally than what happens in the intent service. The key thing to remember in this idiom and the intent service framework, which is going to embody the idiom in reusable code, is that there's only one thread running in the background. That's very important, and you'll see how that plays out later. There's a whole bunch of things in Android that use exactly this idiom. So the calendar has an alert service that uses it. The MMS service basically uses this, and there's a couple places it's used in MMS. So it's a very widely used idiom. The cool part about this, and really the key lesson I want to get across, in addition to just showing you how this all works, is that oftentimes frameworks emerge from looking at commonality that appears in code multiple places, where people say, gosh, every time we do this, we do the same sort of thing. Wouldn't it make sense to refactor the code, make a reusable entity, like an intent service, and then go back and change the existing code to use the reusable code, as opposed to having to re-implement this stuff in subtle ways over and over again? And hopefully you can all see why that's a win, right? Does anybody want to say why that's a win, to spend the time refactoring something? What does that give you? What's the benefit there? maybe a better way to put it, why is it a downside to have multiple versions that do almost the same thing? Justin?
Keeping it consistent is going to get really frustrating.
Exactly. So the main thing is whenever you have more than one of something that does almost the same thing, you have a problem because now you have to maintain multiple things. And if you come up with a better algorithm or you find a bug or a security vulnerability or whatever you do, you have to go to multiple places. And that gets really old in a hurry. And for the kind of assignments you typically do here in an undergrad program or even a grad program where you're going to do something once and then throw it away, not the end of the world, right? If you go out and work in industry, it's a big issue. In fact, at one point someone had gone in to look at some of Microsoft's code base and they found 25 different implementations of the string class in Microsoft Word, right? Which is why it was so bloated, because they had code that was gigantic and they'd never taken the time to refactor it. By the way, another little aside, because it's interesting, Microsoft ended up with this bloatware problem. Microsoft was very famous for a long time of being bloatware, right? Every time you had a new release, you had to get more disks because things got bigger and bigger and bigger. And one of the reasons why they ended up in that situation was that their development process was based on a model called sync and stabilize. And the intent is not a bad intent. The intent is to always be pretty much ready to ship as quickly as possible. So your goal is to keep your code base close to working, so when the release is imminent, you're close to being done, right? And one of the things they do to enforce this is at Microsoft, this may have changed, but back in the day, if you broke the build, in other words, if you checked in code that caused the overall system to break, then you couldn't leave work until you fixed your mistake. So you can imagine people massively coked up on diet caffeinated drinks, running around at 3 in the morning, frantically trying to fix the bug so they can get some rest, right, before they drop of exhaustion. The problem with that model is that nobody is incented to take the time to re-architect and refactor. Because the minute you start to re-architect and refactor, the likelihood of breaking things goes up, and therefore you will be punished. So that's a good example of a perverse incentive system. The kind of thing that Scott Adams from Dilbert loves to write about all the time. So this is about refactoring. So let's take a look and see what the intent service does. So the intent service basically said, hey, let's refactor this code. Let's take this common idiom, which is actually an embodiment of a pattern called the command processor pattern, and let's bake it into a piece of reusable code. And that code is called the intent service. So intent service extends service, so it is a service. And it's really, really easy to use. And probably all those of you who have implemented assignment 4, which hopefully is everybody at this point, you realize how ridiculously easy it is to use. You just come, inherit from intent service, and you fill in on-handle intent, and that's the guy that actually does the work. So subclasses only have to override this hook method. Everything else pretty much is done for you. Getting the request in from an activity is done for you. The on-start command is done for you. The creating a thread and passing the intent between the main thread and the background thread, that's done for you. Stopping the service when it's finished, that's done for you. All you have to do is just fill in the blanks, which is pretty cool. However, the caveat to this wonderful simplified model of things is that there's only one background thread. So that means if that background thread takes a long time to run, then everybody else is going to have to wait. So what's a good example of this? Anybody know a good example of this kind of a model, this kind of a FIFO concurrency model that you might have run into in everyday life? So a good example is going to the drive-in at a fast food restaurant, right? So you're going through the drive-through, and there's, let's say for sake of argument, there's one person who's taking the order and giving the food. Sometimes there's more than one person, but let's say there's one person. So in that case, if you end up getting behind a bunch of other people who have very complicated orders, but your order is very simple, you're just going to have to wait until they're done, right? What would be a way of making that less of a problem? Win. So you, yeah, so you could be kind of hard in a drive-through to do this because the cars would be like smashing into each other as they rearrange the order. But if you went into the restaurant and you had multiple queues, then of course you could go faster. And just like you said, express lines, you go to the supermarket And if you have 10 items or less, you go through a certain line, and if you don't, you go through a different line. At airports, they have a model like this where they break people up by class of service. So you have, first class and business class and coach class and so on and so forth. So there are lots of different ways to do it. But waiting in line in a drive-through is a good example of the kind of concurrency model that the intent service provides and the pros and cons of it. The processing occurs in the processing of the intent occurs off the main thread. That's a win because that way you can block for a long period of time and not get the dreaded application not responding dialog. Now, if you want to process intents concurrently, you can use other models, like you can use executor service or the executor framework. You could spawn threads. For those of you who are doing the grad version, there's other ways of doing this kind of stuff with spawning threads and so on. Once you do that, however, with a started service, life gets really subtle about how you shut the service down, and we'll talk about that a little later. It turns out that you have to really think that through, and it's not at all a trivial thing to do. All right, so the way this is going to work is the client will send intents via calls to start service, and so you call start service, you pass in the intent. If you want to pass more than just the intent, of course, you can put the data into the intent as either data or as extras. The intent service is launched on demand via something called the activator pattern, which you can read about here. Basically launches things on demand. We talked about that before. And then a subclass of the intent service is where the actual processing takes place. So you can see all this, everything here that's not red is stuff that is given to you by the framework, and then the red part is what you have to know something about. The method that runs, the onHandle intent method, actually runs in a background thread, which is spawned internally, as we saw in the internal logic of the intent service and its onCreate hook. And then the Hammer framework is what actually is used to pass the request, the intent, from one thread, the main thread, to the background thread. So then once you've got control, once control passes to your onHandle intent call, then you go ahead and do your thing. Okay, that's pretty much like your program, right? The main difference is that you had to write the logic for this, and you had to do a few extra things because we put a messenger in to the intent. You had to fish the messenger out and then use that to send the results back. Any questions about this? Any questions about your assignment while we're talking about the topic? All right. The intent service itself does a bunch of different things. Internally, it creates a service handler, just like the example did last week. Now it's done for you in the background. And it goes ahead and spawns a thread, which is basically a handler thread, as we talked about before. And then the onStart command is responsible for receiving and queuing intents for the service handler via the Hammer framework and the message queue. So when an intent comes in, it's put into a message and sent to the service handler by the send message call. And then it goes ahead and the thread pulls the stuff out and then calls the onHandle intent method. And there's only one thread. That's really important. Now, when everything's done, the service will stop itself. And this is where it gets interesting. And we'll look at the code here in a second. We'll talk about it in more detail. But the key thing to remember is that when the background thread is done and it calls stop self, is it always guaranteed you need to shut down the service? That's a point to think about. Does anybody have any thoughts on that? Yes, sir.
You said last week that it checks the ID of the intent and
Yep.
it matches the last queued intent, and it'll shut something down, but if not, it won't.
Exactly. That's right. So the way it works, so first we'll talk about how it works, and we'll talk about why it works that way. So what it does is when you call stop self, and we'll see the code in a second, you pass in the start ID that you were given when onStart command was invoked. And keep in mind that this is all done internally by the framework, but if you wrote it yourself, you'd have to keep track of these bookkeeping details. So the intent service framework is doing this under the hood. So it's taking the start ID that came when onStart command was called, and it's calling stop self with that start ID. And if and only if that start ID happens to also be the last received intent, will it shut down the service, in which it calls onDestroy. What would be a circumstance, however, under which those IDs wouldn't match? When would it ever not stop? And this, understanding the answer to that question is the key to understanding a lot about how this service works specifically, but more generally about concurrency. Yes, sir?
Yeah, this question about intent service. So last week you said that if we're going to implement this like through the non-intent service method, then we would need to understand that. But my question is, when would we not have access to the intent service?
Oh, good question. So you would always have access to the intent service. Now, you might ask the question, why, another way to ask your question is, why are there some parts of Android that don't use the intent service but use that idiom that we talked about before? I think the answer to that is probably they were written before they had the intent service, and then they refactored it. So, but the really more interesting question would be if there was some subtle variation that you needed to do in your code that was not handled by the way the intent service worked. That's why you would still end up writing code like this. Not you, but somebody would be too lazy to learn about the intent service. That would be another reason why you might have to write that code. It's almost always a good idea to use the intent service if it's what you need. Now, another way to look at this is it's not always what you need. There's some situations where you don't want to have just one thread. You want to have multiple threads. So in that case, we'll talk about the generalization of this. But I want to go back to the first question, which is what are the circumstances under which calling stop self in the background thread actually wouldn't cause the service to shut down? How could that be the case?
So you start first of it, you start first intent, and you start second intent, and the first intent will just finish for the second intent.
That's exactly right. So I'll reiterate what you just said. So the reason why, and then we'll talk about why that could happen, right? So the basic thing is if the background thread running an intent calls stop self, the circumstance under which that would not shut the service down is if, in the meantime, another intent had showed up, been received by the Android system, but had not shown up yet in the background thread. So how could that be, thinking about the topic at hand, which is concurrency, how could it be that you would have another thing showing up? What's the means by which that would occur?
It's like click download image.
Right, so our particular driver program doesn't really illustrate this at the moment, but we're working on one that will. If you had a list of URLs that you wanted to download, and you basically had an activity that said start service, start service, start service, start service, and kind of spewed them out quickly, then there could actually be a bunch of intents showing up at that service, some of which would be in the queue, some of which would be, or one of which would be processed in a background thread, and others of which may be coming in to the Android framework, but not even put into the queue yet. Right? So there's a number of different scenarios. And the key point I want you to come away with from this discussion is, in a concurrent solution, you've always got to be prepared for things happening, quote, at the same time. Right? So just because the background thread is done doesn't mean something else hasn't shown up. Right? So if you've ever, there's lots of examples in movies that show things like this. If you ever watch the famous, I think it's I Love Lucy show where she's taking pies off a conveyor belt, and the pies are coming too fast, right? She's taking them off and they keep coming and coming. So that's an example where the queue is building up faster than she can take them off. So there's often more work to be done in that situation. All right, so keep that in the back of your mind because we're going to talk more about that when we talk about the implementation. A started service has to stop itself manually, whereas an intent service will automatically do that. When?
Right, so we're going to be talking about how stop self takes the start ID and then does some logic with it.
Yes, we're going to talk about that because I'm going to show you when it's actually, I hate to say it, but stop self in Android is kind of a botch. They kind of did some weird things. It was clearly a hack somebody added to meet a specific use case, and then when they tried to generalize it, it was not obvious, so they left a phrase in the documentation that says basically, if you have more than one thread running in your service, you have to figure out how to shut it down correctly. And I figured it out, so I'll show you, and it's pretty cool. All right, here is a bunch of places that use intent service. You can see there's lots of places that use intent service in Android. All right, so let's, yes, sir?
So if we wanted to use it for the download image service for our assignment 3, instead of extending service, would you extend intent service
Yes.
at the top, and then you get all the, it'll recognize them with service handlers and like. That kind
Yeah,
of
all that stuff is done for you, and it's all hidden magically in the implementation. Yeah. All right, let's talk now about the implementation of this stuff. So basically, it allows you to send these async commands that are expressed as intents and process them concurrently. And it applies a bunch of patterns and idioms to do this. And the most important thing it does is it applies something called the command processor pattern. So that's basically the pattern that's being implemented by the intent service. This pattern, just so you'll see the connections, is also the same pattern that's implemented by some of the Java concurrency mechanisms like the executor service or the executor framework, and it's also implemented by the Hammer framework when you use runnables. So runnables, the Hammer framework with runnables, the Java executor framework, and the intent service are 3 different pieces of code, all of which implement the same pattern, and they do it in slightly different ways. And there are reasons why they're 3 different things, because they don't quite work exactly the same way. All right, so here's how intent service actually is implemented. So it extends service, and then it defines these data members. And what's funny about this implementation is it looks almost exactly like the discussion we had the other day for the hard-coded version of the download image server. This is just what's in the framework. So that's why I said they refactored it. They baked it in to the framework. We use the volatile keyword so that the data members are visible to threads. Here's the onCreate method, which is called when the intent service is first created. It goes ahead and makes a handler thread, starts it, gets the looper, and then passes it to a new instance of service handler, which means that the handle message method of the service handler will now be dispatched in the handler thread. So it's going to run in the background. All right. Here's the onStart command. Keep in mind this is done for you. You don't have to know or care that this is taking place. I'm just showing you how it works. OnStart command is called each time start service is called. OnCreate is only called once. I think that was a question from the quiz last week. Speaking of which, all the quizzes are available. You can pick them up in 226. There's a helper method called onStart, which basically makes a message, stores the start ID and the intent into the message, and then passes it to the service handler via the send message call. By the way, just a little side note on assignment number 4. This parameter, arg1, comes in very handy if you want to communicate something back from the service to the activity. Like what would be something you might want to convey back from the service to the activity? If the result was correct, right? So if you try to download something that's either a bad URL or whatever, and you get a null back, then you want to set message.arg1 to be activity result canceled as opposed to result OK. And then, of course, you check that on the activity side to know what happened. Yeah?
How many args are there?
I want to say that there are 2. This is kind of a hack. I mean, Android, the guys who are doing message were like, oh, yeah, just put a couple of ints in there. Just use it however you want, right? They're integers, yeah. So they work well for things like this, status codes and stuff like that. All right. The handler framework, when it gets send message, enqueues and processes message in FIFO order, which means that a more important message or intent that comes in will just sit and wait, just like the example we did before of waiting in a drive-thru. Doesn't matter how busy you are or how important you are, you're going to wait behind everybody else there. Here's the service handler class. It extends handler. So it goes ahead and has a handle message method, which gets called back, which gets called when there's work to be done. This runs in a background thread, and it just calls onHandleIntent with the object, which was given the intent. So you can see that the intent was passed in object field, and that's what's passed here. You then have to implement onHandleIntent. That's what you do. So you're responsible for subclassing this. And only one intent is processed at a time. So I guess it's kind of like another good example if you don't like waiting in a drive-through, the carpool lane, it's one thing goes in there at a time. Now here's the kicker. Question, yeah?
Is there a limit to how much you can pack into a message?
Is there a limit to what?
To how much you can pack inside of a message?
Well, messages just hold pointers to things, right? So for example, let's go back over here where we set the message. So there's actually other fields as well. These are some of the common ones. So you can put a couple of ints in there, right? That's sort of fixed. And then you can put an object. The minute you can put an object, you can put just about anything, right? And then there's also, I think, a bundle that you can put, which is used to pass things across processes. So there's a bunch of different stuff you can put into a message. So no, there really isn't. But keep in mind, that's only because it's storing a reference to something, not the thing itself. All right, so here's stop self. Stop self is called, and keep in mind this is the start ID that is associated with this intent from on start command. Yes, Win?
So about the bundle remark, why do we need to create a bundle in the first place? And why don't we just have like an array?
So bundles are used to pass things across process address boundaries. That's the purpose of
You're
it.
just passing the reference to the bundle though.
Things that you put into bundles can go across the address boundaries, and they'll be properly marshaled and demarshalled as needed. If you don't use bundles, then you become responsible for doing that yourself. So it's just a convenience to make your life easier. If you don't want to make your life easier, you can come up with other ways to make it more complicated if you so desire. Okay, so stop self. This is used so you don't stop yourself too early when there's still more work to do. And then, of course, when stop self is called, and it is indeed the last start ID, it is the last thing that has been seen, then it automatically calls on destroy, which in this case quits the looper. All right, now what I'm going to do, just because it's kind of fun and I figured it out the other day, I will show you the magic of how to make this stuff work. Let's see if I can first make my font bigger. Let's try 24. That's always a good size. All right. Let's see if we can need to bold it or not. Yes. All right. So let's go ahead and poke around here and see if I can remember where I put it. I think I know where I put it. Okay. I think it's in Vandy, Mook, POSA. All right, this is where I think it goes. Okay, so that might still be a little small for people sitting in the back. Let's see if I can make it bigger still. There we go, that's a little better. All right, so this is an implementation of yet another variant of the download application. And you'll see that what it does is it's going to actually use a thread pool in order to run the requests. Now, for the simple driver program we have so far, this would be massive overkill because there's only one activity that's sent at a time. But we're working on a variant of that where you actually give a list of URLs and they're all downloaded concurrently, and then what you get back is something that can be displayed in the gallery application as an array or a list view worth of images that have come back. So that's where we're headed with this. So imagine we have a client that drives this in some interesting way. So we have download image service, which extends thread pool service. I'll show you thread pool service in a second. That's where all the magic happens. Basically, the way this is going to work is that thread pool service has a method that lets you run things in a pool of threads, as the name implies. And when a request comes in, so let's go take a look at, oh, come on. Oops. On start command, that's what we want. So when on start command gets called, it goes ahead and makes a new runnable. We'll take a look at what that does in a second. And then it goes ahead and it executes that runnable in the background. And the mechanism that's doing this under the hood is something from Java called the executor framework. And the executor framework allows you to have a pool of threads, and you say execute. You take a runnable, you call execute, and that runnable's run hook method is run in one of the threads in the pool of threads. You don't know, you don't care which one it is. So this allows us to be able to do multiple downloads simultaneously. And I'll show you that code in a bit more in a second. Any questions about that? All right, so the make download runnable method, that's the guy that does all the cool stuff. So make download runnable basically creates a new runnable. And the first thing it does is it calls up to a method that it inherits from the thread pool service, and I'll show you what that is in a second, that says, I'm about to start processing this intent in a background thread. And it passes in the start ID. You'll see what that's needed for in a second. And then it goes ahead and extracts the URI and other stuff it needs. And it goes ahead and downloads the file, sets the extra, sends it back, blah, blah, blah. And the last thing it does, no matter how it leaves this thread, is it says, I'm done processing this intent. And it gives the start ID it was passed in. So the key point here is that this run method that runs in a background thread is bracketed by 2 calls that tell some helper service, we started to process something in a background thread, and we're done processing it in the background thread. OK, so that's what we're going to do. Now I'm going to show you the thread pool service. But before I do that, I just want to talk about what problem we're trying to solve here. So the problem we're trying to solve here is stop self, right? When you call stop self, you have to pass in the thread ID of what you've been working on. That works fine when there's only one background thread. If there's more than one background thread, if 2 or more background threads are running, the question arises, how can you call stop self correctly? Can anybody see what the problem is that we're dealing with here? Why is this an issue in the first place? So it's, yeah?
You have to communicate between all these different threads, like to see which node process is running, or
Exactly. So the insight here is when you call stop self, you don't know who else is running. You, the caller of stop self, if you don't do what we're about to do. You don't know if there's any other threads running. Now with the intent service, there was no other thread running. There was a main thread that was running, and some new work may have shown up. And so by the time you call stop self in the background thread, there may already be new work, in which case the service won't shut down because the last received start ID is actually higher than the one that you had in your little hand when you called stop self. When you've got multiple threads running, we'll just focus on 2 to make the example tractable. Now you've got a problem. Imagine that 2 requests come into the service, and we'll say that we'll call the requests 1 and 2 to make it easy. Request 1 comes in, a new thread is dispatched, either spawned or taken out of a pool, and it starts to run. So request number 1, start ID number 1 is running, right? And now request number 2 comes in, and it starts to run, and it's running. If both threads, when they finish, call stop self with their thread IDs, can anybody see a scenario under which the wrong thing will happen? If thread 2 finishes first, what will happen if thread 2 finishes first? It'll stop the service because it had the higher thread ID, right? It had the higher start ID, and yet it came in second. And so if the first guy is still running and hasn't stopped yet, then that will cause the whole thing to shut down, which would be bad, right? Because there'd be this, it's kind of like pulling the rug out from underneath something. That the other thread was trying to do its job, and the whole service just disappeared, which would be bad, right? So the question arises, how can you make this work properly? And it turns out to be rather subtle. So the obvious things to do don't necessarily work very well. And you also have to watch out for the situation where you fail to call stop self, and the service never shuts itself down at all. Okay? So what I'm about to show you is how to do this, which I sat down and puzzled about for a while. I think I've come up with a really good way to do it. So here is thread pool service, which extends service. And thread pool service defines a couple of internal data members, one of which is called set. So a set is a set of integers, and surprise, surprise, they're going to be integers of start IDs, right? And we're going to make this a hash set. You could also make it a hash tree if you wanted to. It doesn't really seem to matter. So this is a set. We also keep track of the last start ID, which is the last thing that we've received. Now this is actually somewhat tricky, and you'll see why we need it. Then we have an executor service, Executor service is created in the onCreate method, which makes the right kind of service, and it's destroyed in the onDestroy method. Here's a factory method that makes the executor service. You can always override this if you want to make a different kind of service. Here's the accessor method that returns the service. here's where things get fun. This is the method that's called begin intent processing. This gets called back when you first start to run in a background thread. And what it does is it uses a synchronized block, which is a very simple synchronization primitive in Java. So what happens when we do synchronize this? Does anybody remember what that does, or anybody know what that does based on things you've learned elsewhere?
Does that just make sure that that block of code runs before anything else in that class, so before another concurrent version of that class is called?
Right. It's basically it's basically a monitor lock, and if you all follow the right protocol, let's assume for sake of argument we all follow the right protocol. When synchronized this is called, then the first thread to get there gets to acquire the lock, the monitor lock as it's called, and then it goes ahead and runs. Any other thread that shows up while the lock is held has to block, has to wait. Tristan.
What's the relationship, if there's any, between a monitor lock and message queue?
You could use monitor locks to implement message queues. So, but they both provide ways of coordinating behavior. That's about the most I'll say at this point. But a message queue, as you might expect, actually has a message, whereas a monitor lock just is used to start and stop something, or let something go and make something wait. A great metaphor that you will never forget for blocking monitor locks and so on is the protocol for accessing a restroom on an airplane, right? So what's the protocol for accessing a restroom on the airplane? You walk up to the restroom, and if the sign says occupied, you have to queue up and wait. And then when the sign says vacant, somebody comes out, another person comes in, they shut the door, the lock goes to, or the sign goes to occupied, right? So basically it's that's a monitor lock. There's one thing that's supposed to be in that critical region at a time, right? One thread, one person, and you wait in line until the one who's using it is finished. So that's basically the metaphor to remember. So by synchronizing this method the way we are doing it, this is actually called a synchronized statement, only one thread is executing this. And the reason we're doing this is because we don't want multiple threads munging with our set. So we go ahead and add ourselves to the set. We're saying, OK, we're here. Record us, please. And then the next thing we do is we update the last known start ID to the start ID that we were given, at which point the curly braces hit, which means that we're done with our critical section, and the method returns. So what we've done is every time you call begin intent processing, you store the start ID in the set. OK, so the start ID is that. What that means is something's running. Here is, whoops. Here's end intent processing, which is a little bit more complicated, but not much more complicated. End intent processing comes along, uses a synchronized block, so there's only one thing going on at a time. It removes the start ID from the set. So it's saying, hey, I'm going away, so I'm taking myself out of the set. It then checks to see if the set is empty. If the set is not empty, what does that mean? There are other threads that are still running, right? Because they haven't come along yet and said, I'm done. So if there's anything in the set, there are other threads running, in which case we say, all right, see you later, we're gone, boom, we return. You're not responsible for doing anything if you're not the last thread. That's what that's trying to say, right? And then if we are the last thread, then we record the last start ID and stuff it into a local variable. And then we call stop self with the last or the most recent thread ID, whatever that might be. So if we're the last thread, then we can call stop self with a thread ID. Now, if it turns out that we were indeed the last thread, but more work has already come in to the service, that's fine, because stop self won't stop the service in that case. So that's why we keep track of the last ID. Jonathan.
So you're keeping a set of all of the start ID, of all of the IDs
We're keeping a set of all running start IDs. Yes.
So why not just keep a counter? So as soon as
Ah.
one comes in, you add one, and as soon as it's done, you subtract one, and you know that there's nothing left when that's 0.
Let's see. This will give us better sanity checking, right? I don't have the code in here at the moment, but you could basically put some checks in there to see if somebody calls end processing with a start ID that doesn't exist, you could throw an exception. Whereas if you use the counter, you couldn't give that kind of error handling. Tristan.
That's the same thing last week, Chris, and you said that it was more useful for debugging.
Well, so debugging or error handling, right?
Okay.
So this is going to tell you, you could actually check to see, you know, if somebody says begin start ID or begin intent processing, some start ID, then later calls end intent processing and gives some nonsensical start ID that was never used, you could detect that with this, whereas a simple counter wouldn't be able to figure that out. Win.
So last start ID is the ID of the last thread to be.
The last intent that's been received. It's not a thread.
Well, last intent that has been received.
Yes, it has been received by a thread that's running, which is different from the last. This is the part that makes it so subtle, right? The Android framework is receiving intents concurrently to the background threads that are processing them.
Okay.
So at any given point in time, the background threads may think, oh, the last start ID was ID 100, right? But Android would say, no, it's 101, right? You haven't seen that one yet. I haven't given it to you, so you wouldn't know about it. So that's why you have to do some of these things. That's why I said that the way that the concurrency model works in Android is kind of a hack. The stop self model is kind of a hack. And it's premised on there only being one thread running in the background. So this mechanism I'm showing you here is a workaround or an extension that allows you to be able to have multiple threads running and then handle them in a clean way.
Right. So why does last start ID matter? If we just want to handle IDs that have come in,
Uh-huh.
why don't all right? So let's say we have 100 threads that ran already.
Yep.
And the thread with the start ID 1 was the last to finish.
Yep.
So we call super dot stop self 1. And by the time we call stop self, there's been a intent 101 that's come. So it doesn't stop because the 1 is less than 101.
Yeah, but so I thought about that when I was doing my implementation. The problem that you have with that model is either you shut the whole process down or you fail to shut the process down. So in one case, if thread 1, if start ID 1 is the last one to finish, then start ID 99, let's say that was the last one, that's already finished, right? So if you called stop self 99, that was the last ID. So the whole thing would shut itself down at that point. If you fail to call the last one, then it won't shut itself down under the scenario you just described. Because
M last start ID is the biggest one that was.
the biggest one that's been seen by our little framework here, but that may not be the biggest one because Android might have one in its pocket it hasn't given us to know about yet.
So why do we need a set then? Why don't we just use a stack and then when this just pops stuff out?
Well, because they finish in different orders, right?
But it doesn't matter. The only thing we need to keep track of is the biggest one that we received.
Well, we are keeping track of the biggest one we received. That's what last start ID is. But the
That's
stack,
that's not gotten from the set.
no, it's not gotten from the set. We don't need it from the set. The set is keeping track of which threads are running. And as we were just talking about, the reason we use a set is so that we can do sanity checking in case someone tries to remove something that's not in the set, in which case we know it's a failure.
But if we didn't want to do sanity checking, we could just do a counter like, all right, these
Right.
threads are running. Okay, cool.
Yep, because we're not actually using the start ID for anything. We're just keeping track of the last one. We're just using it for
Right.
sanity check.
I was bringing that up because I was thinking this like sets take a lot more resources to implement than a counter.
In the grand scheme of things, keep in mind you only have elements in the set as the number of concurrently executing threads,
Yeah.
right? So which is probably very low, like 3 or something like that. So if that is the reason why your program doesn't work, you probably need to spend a penny and buy more memory, right? Did you have a question?
Yeah, so if you call stop self on an ID that's not running anymore, does it still stop?
That would be, if you call it on an ID that's not running and it's not the last one, it's kind of harmless. It just ignores it. If you call it on one, it's not a problem to call it on one that's not running. That's okay, as long as it's not the last one, in which case it'll shut the service down. But if all the other threads are done, then you're fine. Kevin?
I think it was on your previous, on the start method, you had it, the return type is int. I was just curious why you chose, I think it was, yeah, begin intent message. Why did you choose to have it return a value?
Why did I choose to have it return a value? Probably because I should do this. There was probably, oh, I know why. If you take a look, this is insane. If you take a look at stop self, there are two versions of stop self. There's stop self and stop self result. Stop self does not return a result. Stop self result returns Boolean, true or false. And there's actually a reason for doing that. That way you can know whether you're actually going to stop the service, because a lot of the Android services, when they find out they're going to stop, do something else to get themselves restarted later. So I was thinking at first about mimicking that kind of behavior. So I was having return values, but then I decided that was too clever for its own good. So I backed away from that and forgot to change the signature. But thanks for pointing that out.